think we'll be starting in like a minute. Everyone's day going so far. I'm doing okay if any of you are asking, although I don't know if you are. Anyway, this class is going to be about solids or like think of it as 3D geometry. As pointed out, the past three classes have all just been the past few classes only been about geometry, and I'm going to show you that I don't think there will be much geometry from here on out. I just wanted to lump the whole subject into one sort of group so you don't skip around and it's easier to just focus, if you know what I'm saying. So we can get started. I think the main focus of solids as a whole in this level is just understanding some of the properties of each shape and all the different kinds of 3D shapes you'll see, and how to change a 3D problem into a 2D problem that you're more familiar with. And yes, so here's a table of these common shapes. I'm just going to go over them because I didn't make this table. So first we have a cuboid, or basically a rectangular prism, which I'll combine with a cube. Like that. And it's really just you can make it if you take any kind of rectangle and just, so think of taking a piece of paper and just stacking it on top of each other over and over again until you just have a block. And similar to that reasoning, that's how you would find its volume. And the volume of a 3D shape is just how much space it takes up. As you know, area is just for a 2D shape how much space takes up. The volume for 3D. And the volume formula for a rectangular prism is just you multiply the dimensions. And this is pretty intuitive because you can think of it as taking this one area and then just stacking it this number of times. Or let me, sorry, I'm annotating again. But well, either way, this is how you do it. And then the surface area is another thing that you'll be asked to find a lot, and that is just if you add up for all the faces, add up the areas of all the faces. I mean, so for a cuboid, you would just take length times width for this face, and then do it for the other 5 ones, and you add them. I'm not sure if I have to go over why that's the case because I think it's pretty intuitive. And the property of the volume equals to base times height for any prism. And what do I mean by prism? Prism is literally just any shape. It doesn't have to be square or rectangle. It could be a triangle, hexagon, pentagon, anything, and just extended into like a block. So a hexagonal prism would it's sort of hard to draw, but if you can understand what I'm drawing, this is what like a hexagonal prism would be like. And the volume would just be base times height because you can just think of it as stacking lots of hexagons until you create this shape. And you're just stacking the height number of pentagons. And they all take up the same amount of area. Anyway, so next one I want to talk about is the pyramid. And the pyramid is sort of interesting in that it's like almost like a 3D kind of triangle where you have a base of any shape and then a single vertex point V that is connected to each of the points on the base. And you would find the area of volume of this shape by doing base times height over 3. Now why is this? Well, it's sort of hard to prove, but basically the idea is that in a two-dimensional shape, a triangle is going to be half the volume of like half the area of the rectangle, which is why it's base times height over 2. So in 3 dimensions, it's going to be 1/3 of the corresponding prism. Similar to how this is half, is just going to be 1/3 of the prism. And that's how you'd find the area of any kind of pyramid. Base times height divided by 3. I just want to mention that a special case of a prism and a pyramid are the cylinder and the cone. And they have the same properties for volume as the prisms and pyramids do. Okay. Please. Okay, we'll go over the sphere later. I'm not actually entirely sure the proof of these things, but they're just facts at this point. So anyway, where was that? Okay, so the interesting part about these cylinder and cone is that these are circle based. We'll talk about these later, right? So how would you be able to find the surface area of them if there's really no great formula for how to find the surface area of the, so you can think of it as like the smooth part of the cone and the cylinder, as it's just a circle all the way down, right? So basically the method you would use to find the surface area of a cone, yes, is you have to know what the height of the cone is, and you have to know what the radius of the base is, right? Basically the method is, one, you need to find the circumference of the base. And then 2, you need to know slant height. Okay, and slant height you can just find using Pythagorean Theorem with the height and the radius. Now here is where one of like the imaginative concepts of these solids comes in, where I claim that you can make a cone by taking any kind of sector of a circle. For example, it can look like this, or it can look like this. It doesn't really matter. And you just connect these two edges. And then when you do that, I can't demonstrate, but you can try this on your own. Just cut out a circle and then cut out a sector of it. When you tape together these two edges, what happens is you'll make a cone that looks like this, where the base is just going to have circumference of whatever this length is. This can be circumference of the base, and then the radius is going to be the slant height. So basically, the slant height is to find the radius of this sector, and then you use the circumference. And since you know the radius, you'll know the circumference of this entire circle. And after that, you would use the circumference of the base to determine the angle of the sector that is missing. And then you can calculate the angle of the sector that is not missing. And after that, you just use the formula for the area of a sector that I gave you in week 1 for the area of this lateral surface area. And then you just add that to the area of the circle, and then that's your total surface area. That can be so confusing, so I think I'm gonna give you just some numbers that you can work with. Okay, please stop annotating. Thanks. Okay. So say we have a cone, radius is 4, let's say, and its height is 3. So what is the surface area of this cone? I'm gonna let you guys work on this for like a minute, and then you can message me what you get. I don't know. give an answer later. Okay, will someone raise their hand?
So I had a quick idea. Like, we're trying to find the surface area of the cone, right?
Yes.
So basically, just like find the area of the circle, which is going to be 16 pi, and then you have to find the area of the actual cone part. So you can like roll it out, and basically it would be 3 times 8, if I'm right. Am I right, Brian?
Can you say it again?
So basically what will happen is like you have to roll out the top part. So 1 minute, let me just draw. Okay, so the bottom part would be 16 pi. And then this top part, if you roll it out, it would be about 3 by the circumference of this thing, which is gonna be 2 pi r, which is gonna be 8 pi. So it would be 24 pi plus 16 pi, which is 40 pi. Am I right?
No, you're not. The reason why you're not right is because you're sort of assuming that you're treating this cone as a cylinder when it's really not. As in, I'll give an example. So what you're doing is you're taking this base, right? And you have a height of 3. So what you're doing is you're taking the surface area of the circle plus the surface area of what a cylinder of the height of 3 would have. As this, as I mentioned before, this lateral surface area of a cone is not shaped like a rectangle. It's shaped like a circle with missing a sector, right? But think about it this way. You can, say you take a piece, I don't know if I can with this, if you take a piece of paper, right, and you roll it, you'll make a cylinder, okay? So then what you're doing is you're literally just taking the lateral surface area of the cylinder, because when you unroll it, it's just a rectangle. But with a cone, it's different. When you unroll it, you can't really unroll it because it's all comes together at one point up here. And that means that it's actually going to be a circle because each of the points on this base is equidistant from the vertex. That's how you know that it's going to be like a sector. So anyway, circle. And we know that the circumference of the base, you erase that part, okay.
The circumference would just simply be what's it called? 24. 8 pi, right?
Circumference is. Can you let me talk for now? pi, and we know the slant height is 5. So that means the circumference of this whole circle that we mentioned here is going to be 10 pi. So the ratio of the base to the circumference is going to be 4/5. And this means that the area of the lateral surface area is going to be 4/5 of if it was just a complete circle, in which it would be 25 pi. So total surface area would be 20 plus 16, which is 36 pi. Okay, question, what is the slant height? You can think of the slant height as, this applies to both a cone and any kind of pyramid, where if you have, it's literally just the distance from the vertex to the base, like that. Like, it's, the slant height is equal for every single point on a cone because the distance from the vertex to the circle is the same. But for a pyramid, am I blanking out? It look like it. For a pyramid, the slant height would just be the height of one of the triangular faces of the pyramid. Okay. Okay, moving on. Okay. I don't know what drawing software do I use. This isn't like a drawing. This is just an online whiteboard. Unless you're talking about the table, I got that off Google Images. Don't worry about it. But yes, this is just scratchwork.io as a online whiteboard. So yeah. Anyway, next controversial topic, the sphere. It's weird because it's just a 3D circle, as you might describe it. And why is it this? Please stop annotating things. Wow. Okay. Either way, the sphere is strange in that it's sort of hard to figure out what its area and what surface area and volume is going to be. I don't know how to disable them. That sort of sucks, but I can clear them whenever I want. Yeah. Anyway, I'm not going to show you why any of these are true, but it's very important to know that the volume of the sphere is 4/3 pi r cubed, and the surface area is going to be 4 pi r squared. And you notice that volume and surface area, they're scaling off of r squared and r cubed respectively. That is actually not a coincidence, generally speaking. Actually, I'll get into that later. Anyway, where was I? So, if you were studying the table, there were a few shapes that I think were left out. One of them is a tetrahedron, which is a triangular pyramid, and I like it because you can think of it. You can basically use any face as its base, and there's only one other vertex that can be the vertex of the pyramid. And its volume is still calculated like any pyramid, except, yes. All I have to know is that for a regular tetrahedron, a regular one, means that all faces are equilateral. And when you drop the height from the vertex to the base, you always hit the centroid of the triangle. I believe this might be true for any kind of triangular pyramid, though, as well. Don't quote me on that. More. Oh look, I can disable it. That's interesting. Okay, well, you guys can try to annotate now. I don't know if you can. Okay, and the next one I want to talk about is the octahedron. And like as it sounds, it has 8 sides, or 8 faces, I mean. Octa means 8. And basically it's just 2 pyramids stacked on top of each other. Not on top, but like you have their faces glued together, and usually the square pyramid. So for a regular octahedron, you just find the volume is just twice of the pyramid. And then the surface area is just going to be each of the triangles added together. Yes, if there's a question asked for an octahedron, this is what it looks like. It's not really the most common shape, but it's still quite interesting. And one thing I forgot to mention in this paper is probably the only formula you'll really need to know about general polyhedra, which is Euler's polyhedron formula. And here, a polyhedron just refers to any 3D shape with straight edges and no curves, similar to the polygon but in 3 dimensions. And so if for all convex, which basically means that it doesn't like cave in, it's more like a ball shape, so to speak. That's not a very rigorous definition, but you can just think of it that way. For all convex polyhedra, you'll have a special relationship between the number of faces, the number of edges, and the number of vertices. We can take a cube, for example. A cube has 6 faces, 12 edges, and 8 vertices. I forgot to write the formula. Formula is basically faces plus vertices equals to edges plus 2. This will work for all convex polyhedron. And then if it's has a hole in it, it's different, but we don't go into that. But yes, this will be true for any convex one. You can try it. You can try to apply this to any of them. Like if you take a tetrahedron, for example, it's 4 faces and 4 vertices and has 6 edges, and that works. So you'll see some problems just utilize this fact to make it a lot easier to solve. And there actually is one problem that does use this somewhere down here, although it's not entirely required. It's nice to know. Next thing I want to talk about is truncated shapes. Basically, truncated usually refers to a pyramid or a cone, and it's literally just you cut off the top of the shape, so you sort of have like a 3D trapezoid of some kind. For example, a truncated square pyramid, or a rectangular pyramid if you really want, would just be if you cut off this top part right here, so you'll end up with this kind of shape. And it's important to know that the top base and the bottom base, they are indeed parallel, or else it wouldn't be a true truncated shape. And the only way to find the volume of this shape would be to like assume that it's a full intact pyramid and subtract off this missing part. You can't really find the volume of this directly. And the same thing with the surface area. You can sort of find the areas of this base, but you'll need to be able to figure out this base as well, and then you can just add the areas of the trapezoids here if you know all the measurements. The surface area itself is not that big a problem. Volume is. And here I think is also a great time to mention that how ratios of volumes of similar solids work. So you maybe think that similarity only applies to 2 dimensions, but it actually applies to 3-dimensional shapes as well. So I'll put this here. Similarity. It's sort of the same concept if they have the same, if they're the same shape but on different scales, like a cube with side length 1 and a cube side length 2. They're similar. So similarly basically says that the ratio of the volumes of two similar solids is going to be the cube of ratio of side lengths. And the ratio of the surface areas is going to be equal to the square of the side length ratios. And you can think of this as in 2 dimensions, you'd have the ratio of the areas is equal to the square of the ratio of the side length. So it sort of carries over into 3 dimensions as well, where it's just the cube now, since you have 3 dimensions. Now, general tips to solving these kind of problems. You can draw a decent diagram. It's sort of hard to draw, but if you have something that you can work with, it makes the problem a whole lot easier. As usual, Pythagorean Theorem is very prevalent in geometry problems, and no exception for solids. So you can always use it to find certain heights or slant heights. That is often the case. If you're asked to find the volume of something, you can always try to shape it into 2 different volumes if you're not comfortable with just finding it directly. I find another thing that works really well is working backwards. By working backwards, I mean you start at what is the problem asking for, then you look for the requirements that you need to get what you want. So you can basically start by saying, oh, I want to find the volume. Well, what do I need to find the volume? Oh, I need the side length. How do I find the side length? Oh, well, they gave me some of these other values, so I can use that to find the side length, and so on. It's easier to sort out the direction of your ideas, and it saves time as well. So when you know what you're doing, efficiency goes up, and vice versa. And the converse holds true as well. Anyway, but I think the biggest important thing to keep in mind: don't try to reduce the number of dimensions. Don't keep it in 3D, as it's sort of hard to work that way. Always look for cross sections, which basically means that if you like take some kind of knife and just cut the object, and then you can just take a look at what the surface looks like, or in less casual terms, you cast the shape onto a plane, and then you can use 2D geometry stuff to figure it out. Now, what I mean is, for example, a cross section. Let's say we want to take a cross section of a prism for some reason. Let's say it's a triangular prism. Okay, the cross section would just be like if we took a plane and just it's really hard to draw, but you can sort of cut it down the middle like that. So you'd just be left with a triangular cross section, as it's just like one small excerpt from the original solid. And this is very useful because it greatly simplifies the problem. And simplicity is often the best you can hope for when it comes to geometry. Yes, and then final thing is inscribing. Inscribing solids works similarly to a 2D plane, which means that tangent rules apply. And by inscribing, it generally refers to putting a sphere into weird objects, or putting a sphere into a cube. You can inscribe it. That's actually a great example, actually. So if we take a cube, we can basically inscribe a sphere so that it is tangent to every single face. So by tangency will still apply, it means that the line from the center to the tangency point of each face is still going to be perpendicular to the plane. And then we can actually take a cross section of this to get a square and a circle that's inscribed inside of it. So that is a cool way to combine these two. Anyway, we can start with the problems now, I think. Okay. Oh yes, I would just like to state that tetrahedron here it's not regular, it's literally just a triangular pyramid. So we have a solid tetrahedron is sliced off a solid wooden unit cube by a plane, and it passes through two non-adjacent vertices on one face and one vertex on the opposite face, not adjacent to either of the first two vertices, and then it's just basically cut off and thrown away, and the cube is put on the table. So that's a lot of words, and it's often a lot easier to just draw it, and that makes the problem a lot easier to understand. Here we have two non-adjacent vertices on one face, one vertex on the opposite face, not adjacent to either of them. So since we know that this will work no matter what vertex we choose, without loss of generality, we can just choose this one and this one as our two non-adjacent ones. Now, one vertex on the opposite face not adjacent. So it's either this point or this point. Since it's symmetric, it does not matter which point we choose, as this quantity that we want to find will not change. So I'm just going to choose this one because I want to, I guess. Let's say we cut this off, and we're just left with a weird kind of cube. I'm not going to draw it, but I'll let you imagine it. It's just a cube where the entire corner is just not there. I want to find the height of this object. Well, we can write the height of the object as just the difference of the height of the cube if it was placed like that, but without the thing cut off, and subtract it from the height of the tetrahedron. You can't do that. Basically, what we want to do is so we already know the space diagonal, actually we don't know that, but space diagonal of a cube is basically the length from vertex to opposite vertex here. And this is going to be the side length times the square root of 3. This can be easily seen because we can use Pythagorean Theorem twice using this side and this side, which is s square root 2. This is s, the space diagonal is s square root 3. And then it says the unit cube, which means the side length is just 1. So we can take away that. Now we just want to find the height of this tetrahedron. We can take it out of the diagram. So it sort of looks like that. We know that this is an equilateral triangle, the base of side length square root 2. And we know that each of these sides have length 1, since they are the complete side of a unit cube. So we want the height of this pyramid, right? And the special thing about tetrahedron is that you can use any side as its base. So if we find the volume using two different bases, then we can find the height. Since this is a cube, we know that everything here is at right angle. So the volume using 1, 1 square root 2 triangle as the base and 1 as the height is just going to be 1/6, because 1 times 1 times 1 times 1/2 and then times 1/3 is 1/6. And the volume, this is also equal to the area of the equilateral triangle times height. The equilateral triangle's area is going to be, if its side length is s, it's s squared root 3 over 4. It's just a formula for it. It can be easily verified by just using Pythagorean Theorem, but we'll just skip that because it takes time. Plus, and then times the height divided by 3. And then after a bit of simplification, you can find that s squared is just 2, so this is just 3 root 3 over 2 times the height, I believe. Nope, this is not. It's root 3 over 6, because, yes. Pay attention, I guess. square root 3 over 6 times the height. So then 1/6 equals square root 3 over 6 times the height. This means that the height is just going to be 1 over the square root of 3, or root 3 over 3. So now we can just subtract these two, so we get the total height is just 2 square root 3 over 3. One thing that I did forget to mention about this problem is that technically we don't know that the space diagonal and the height are in the same line just yet. But basically, you can just use symmetricity, and you know that the centroid of equilateral triangle is like the center of literally everything for the triangle. So you know that this diagonal, which is also splitting the cube in half, will go through this point as well. You need a more rigorous proof to actually show this, but you can think of it intuitively like everything's symmetric, therefore it has to go through the center. I did get a question of what a cross section is again, and I just want to say that it's sort of hard to explain, but basically you usually want to take a cross section of a notable place in your diagram, and it's really just if you take a plane, and a plane is what you just call like a piece of paper is like a plane where it's two-dimensional, and then you can just put a two-dimensional image on it. So you want to basically just take a piece of your diagram out and not have it in 3 dimensions. So a cross section, for example, a cross section of a cylinder would be like, well, there are multiple ones you can take, but one cross section you can take, let's say you want to take like a cross section in the middle right here, right? So let's say you just draw like a plane like this, and then if you look at what the plane has, it's just going to be a circle. That'd be a cross section of a cylinder horizontally. If we take a vertical cross section, which is basically, let's just say we put a plane, just cut it right down the middle, what you'll find is that this vertical cross section is actually a rectangle. So it's just a template we can use to simplify the problem, and you don't always use it, but when you do, it makes life a lot easier. Anyway, this problem, a solid cube of side length 1 is removed from each corner of a solid cube of side length 3. How many edges does the remaining solid have? First thing you should notice about this problem is that these side lengths are not entirely relevant, are not relevant at all, because we know that, well, 1, when you take away the side length 1 and the whole thing is 3, it's not like anything will, I'll just draw it. But since 1 is less than half of 3, it really does not change much. So basically, we'll basically take this cube and we'll just cut off this corner right here. You can just think of it as this part being gone, right? And this is for all 8 of the corners. So it's asking how many edges does this solid have? And you can do this in many ways, but I just want to go with I just mentioned the Euler's formula, or it's the Euler's Alphademic formula. We can just use this method as a good exercise. Not 54, unfortunately. Okay. Basically, we know that F plus V equals to E plus 2, right? So we want to find edges, so we want to know the total number of faces and total number of vertices. How many faces do you think this thing would have? That is a completely rhetorical question. The number of faces it has is 6, plus then the number of faces added for each cube that's removed. That would be 3 times 8 equals 30. And you can actually, I think that's right. Basically, you can think of it as that removing a cube does not change any of the original number of faces. So you're just left with 3 extra faces from where you remove the cube for each vertex. Now the number of vertices. You start out with 1 vertex here, but when you remove the cube, you make 1, 2, 3, 4, 5, 6, 7 new vertices. And this applies for each of the 8 vertices. So you go from 1 to 7. So now you have 56 vertices. So your total number of edges is going to be 30 plus 56 minus 2. And it's equal to 84. There is another way you can do this, where you just skip this formula part. And let's just say that, let's just redraw it. Another way you could do this. I did not mean to draw that. So you want to take this out again. We can just count the number of edges straight up. Currently there are 12 edges in this cube. So for each vertex cube that we remove, we add 1, 2, 3, 4, 5, 6, and you have 7, 8, 9 edges. So 12 and then plus 9 times 8 is going to be 84 as well. And these are the same. We know that this answer is right. And any of the answers that you sent me were wrong. So yes. This is number 14. So it might seem a bit on the easier side, but a lot of times they can be sort of tricky. So you really have to be careful with what you're counting and make sure you're not missing anything. All right. This one is actually one of the more difficult ones. You have 6 spheres of radius 1 are put in a basically hexagon shape, and then we have that they're all internally tangent to a big sphere, and we put another sphere that is internally tangent to the big sphere, but tangent to every single one of the other small ones, and we want the radius of that sphere. So this is going to be a cross-section problem, and it's sort of hard to draw, right? First we can somewhat ignore the circles themselves. Only think about what their centers are, because when we know the center and radius, we can already determine what each of the spheres are doing. We know that they all have radius 1 and they're in hexagon of sine length 2. This means that the centers form a regular hexagon with sides of length 2. And we think of this as I'll touch that later. So then now we want to think about what this large sphere is. It's tangent to every single one of these circles, right? And we know that its center is a centered hexagon. Since each circle reaches out one unit as its radius. For example, if we draw this, we know that this circle has to be tangent like that, and then you can just imagine what it'd be like. So you know the radius of this large circle is going to be 3, which is 2 plus 1. So we already know that the big radius is 3, small radius is 1. We want to know now we can't use this diagram again because a sphere is on top of all of these other circles, so it's not in the same plane as its cross section. And I just want to say that this diagram right here is, let's just assume that this is the big circle, the super big circle, the 7th circle, right? This one. This cross section is just going to be a plane that goes through this circle right in the middle, that contains the diameter of this big circle. Well, they all do, but you can think of it as if this is just a ball lying on a table, it's going to be the plane with the biggest circle that you can make when you cut through it. Or easiest way to think about it, this is the equator of your sphere. So this is what you'd see at the equator. But so now we're going to take this vertical cross section, or I don't really know what we call this, but we can call it like well, let's just say it's vertical cross section. There's really no great name for it. So what you'd have here is let's actually just okay. This is sort of a vertical cross section, except for actually it's not going to be like top down. What's actually I just did not do this. It's more going to be like if we take it from the side. It's hard to explain, but I can once I draw the cross section, I think it'll be easier to understand. It's where if we let this point be one of the centers of a small circle, and this be the center of the large sphere. You know, this length is 2, and then if you extend 1, this is going to be like the radius of this larger sphere. We know that we're going to have another circle whose center is here that is tangent to this large sphere, but also tangent to this small sphere right here. So we can just draw this, you can think of it like that, not like that, but you can just say that it's tangent like this, and then we have the biggest circle that goes around both of them. We know that this line right here, this is going to be perpendicular, and we know this because the center of the A-sphere has to be directly above the center of the hexagon, as it is symmetric. Symmetricity is a very powerful tool. So if we let this length be r, right, we know this entire radius is 3, this length is 2, and we can just connect the centers so that this length is r plus 1, right? So what we have here is that we have a really cool right triangle, and this length is going to be 3 minus r. And you can see it says it's the large radius minus r. So what we basically turned the 3D problem into just Pythagorean theorem. So 3 minus r squared plus 2 squared equals to r plus 1 squared. So from here we'd have r squared minus 6r plus 9 plus 4 equals r squared plus 2r plus 1. R squared cancel out. If AR equals to 12, and R equals to 3 over 2. That is the answer. So just like to emphasize how we solve this problem, and we basically take multiple cross sections to be able to identify different points of information that you need, and then once you have that, you can just create some kind of equation for you to solve for the radius. And generally speaking, I think I mentioned this before, when you have a lot of tangent circles, you're gonna want to look for a Pythagorean theorem regarding the radii of the circles. So yes, if you're going to review any problem in this set, I would recommend looking at this one. It's very interesting. Another cross-section problem. 4 cubes with edges of length 1, 2, 3, 4 are stacked like this. What is the length of the portion xy contained in the cube with edge length 3? Now, there's really no great way to do this directly with the diagram we have, as it's sort of hard to imagine what this line is going to be like and what it passes through. Like if you think about it, this is what xy is. It's just a bit more straight, but you get the idea, right? So what we can do is we can take a cross section. First notice that since these are all cubes, and therefore, if we take a cross section that goes of the plane that goes like through the diagonal of each of the cubes, we'll be left with a triangle like this. That just goes x, y, and then let this point be z, this point like z. And I just wanted to mention that this is not, it is not this. It is not like a triangle that's on its face. That's not what this thing is. This space zy is actually going to be the diagonal of the bottom face of the side of the cube times 4, which is going to be 4 square root 2. This height is 1 plus 2 plus 3 plus 4, which is 10. So we can find that xy is the square root of 133, I think. I'm not entirely sure yet, but no, 132, right? Yes, 132. And this is equal to 2 root 33, right? But still, we're not done. We want to find the part that's contained in the cube with edge length 3. Now, what does that even mean? We have to somehow figure out what part of xy is going to be the length that we want. And what this means is that we need more lines, because there's no way to know with what we have right now. So what we can do is that we can draw these horizontal, actually we can't draw horizontal lines just yet. So you think about it this way: the section of this length that is in each cube is going to be directly related to different segments on xz. So we divide xz into lengths of 1, 2, 3, and 4 like this, and draw horizontal segments. We'll have that this segment is the part that's in cube of science 1. This one is 2. This one is in the 3rd, and this one is in the 4th. And you can actually, it's pretty easy to imagine this as the height just corresponds to the section of the length that's in the cube, like that. From here, this is just basic similar triangles. We have that. Let's label some points. Let's call this A, B, and C. Then we want to find BC, and that's just equal to XC minus XB. You can see here, it's just this length minus here. Actually, you don't even have to do that. Never mind, you don't even have to do that. Although, this might be skipping some steps, but basically, we know that each of these lines are parallel to the base. I believe it's called side splitter theorem, although this is a bit more of an application of it. Where we can just directly say that this length BC over XY is just going to be equal to 3 over 10. And why do we know this? Well, the way you get this is actually just going XC minus XB, and because XC minus XB over XY, and that's going to be equal to this length minus this length over XZ by similar triangles. So then we know that the difference is just 3 over BC, like that. So and after we not cross multiply, but we can swap these terms, we'll just get that BC over XY is 3/10. So BC is just 3/10 of XY. Which means that BC is just 3 root 33 over 5. Voila. I'm running out of time. That's not fun. Okay, here's a cool octahedron problem. When the centers of the faces of this rectangular prism are joined to create an octahedron, what is the volume of the octahedron? First, we have to figure out what the dimensions of it are to be able to find its volume. So we take the centers of each face and just connect them like so. We'll sort of get this kind of shape. Right? And we know that this center shape is going to have a diagonal of just the side length of 5 and 4. This long diagonal is 5 and the short diagonal is going to be 4. Like this is going to be what we call the base, like that. This is 5. The whole length is 5 and the whole length is 4. And why do we know this? It's because, well, the vertices are just the center of the faces, so the line through the center of the face is just going to be equal to the parallel side length. So this is 4 and 5. You know, the area of the base is going to be 10. I mean, no, it's not going to be 10. It's going to be 5. Wait, actually, it's going to be 10. I do know it is going to be 10, as the area of a rhombus, I guess in this case, where the diagonals are perpendicular, is just going to be the product of the diagonals divided by 2. So now what we want to find is the volume of the octahedron, right? Actually, did I miss something here? No, I didn't. Okay. The volume of the octahedron is just going to be the height times this height times the base times, no. Sometimes I really wonder what I'm doing. The height as in this whole height times the base times 1/3. And it's only times 1/3 because we consider the height to be the sum of the height of this bottom pyramid and the sum of the top pyramid. So this is why using the distributive property to combine them. This is only 1/3 instead of 2/3. You know, the height is just 3, so the area is just going to be 3 times the base times 1/3, which is still going to be equal to 10. And that's it. We have 3 minutes left, unfortunately, which means I didn't. Okay, well, we're definitely not going to get to challenge problem today. I guess I'll just cover this one last problem, and I'll post video solutions to each of these two later on. Okay, sound good? You can't answer me, so I'm just going to assume that you said yes. Okay, a sphere with center O has radius 6, and a triangle with sides of length 15, 15, and 24 is situated in space. So each of its sides are tangent to the sphere. What is the distance between O and the plane? So first we want to see what this kind of looks like. And basically what we have is like a sphere, and we can like draw a triangle like that or like that, right? So that it's sort of like a hat almost, where it's a hat except for it's a triangle. Where if this is the head, like how far does it go down before it gets stuck? And again, it's hard to approach in 3 dimensions, so you want to take a cross section. And clearly here, in the best cross section you can take is where the triangle is just a horizontal one that includes the triangle. So this cross section would just look like this. As the cross section of a sphere is just going to be a circle, right? The radius, we don't know the radius of this cross section here. We know the sides are length 15, 15, and 24. So we can use the formula for an in-center to find the in-radius. We find the in-radius. And very interestingly, this is going to be a 9, 12, 15 right triangle, 3, 4, 5. It's almost as if they made the problem like that. So the area is going to be really easy to find. It's just 108, and the perimeter is 54. So we know that the in-radius is going to be 4. It's 2 times the area over the perimeter. It's going to be 2 times 108 over 54, and that's equal to 4. So the radius of this small circle is 4. Like, that's great and all, but we want to find distance between O and the plane. So this means that we need a vertical cross-section that includes the center O. So if we draw this again, and the vertical cross-section is still going to be a circle since it's a sphere, and we know that we have this weird circle here as radius of 4 that is also going to be let's just call this point I. We know that I is going to be this point in the cross section, so it's not 3-dimensional, and I don't have to draw it like this. But we're taking the cross section, and we know this point I is here, such that the distance, such that I has radius of 4, which means that each of these lengths is 4, like so. And we know that O is here. So we only need to find OI in this case. The class is going to end like now. Okay, well basically, we know that this point, this is 6, this is 4. By Pythagorean Theorem, this is going to be 2√5. And you can, yes, you can check that, but this is the answer. And this does seem a bit rushed, but basically, the point is the distance. Well, first, how do we know that I is going to be the point where the OI is going to be the distance to the plane? The reason why we know this is because we took the cross section earlier, and I is the center of that circular cross section, which means that it's going to be the point closest to the center. And I is on this plane, so an OI is perpendicular. So we know that this class is over, I guess. Although my internet connection is stable. That's great. But, class is technically over right now. So if you want to leave, you're free to go. And I'll just put solutions to these two problems up a bit later. Okay.